customer engineer at Google Cloud, and I work with digital native customers across India. I also work with the Cloud AI Solutions team as an SRE, a site reliability engineer for a 20% project. At Google, you get this option of spending 20% of your time on a project that is not part of your team, maybe for your core role. So that's the 20% thing. And I want to thank you all for being here and thank the Cypher team for organizing an in-person event. It's great to meet people in person, especially after virtual coffees for 2 years now. And over the past 2 years, apart from virtual Dalgona and whatnot coffees, a lot of other things have changed. And one of the most major changes has been the move to cloud. We are all aware how the pandemic accelerated this move, right? When we were on-prem, the components were fixed. When we move to cloud, it's different. We are scaling up and down as needed. We can possibly hand off operational overhead to cloud if used the right way. My question to you is that we've changed a lot of things, but have we updated our ways of building applications for cloud? Or is it just another traditional architecture picked from on-prem, positioned on cloud as it is? So today I'm going to talk about how to make the most out of cloud and avoid the pitfalls of old approaches into a new platform. And if you're wondering what's in here for you, maybe you need to know these ways to not spend majority of your time on the non-ML parts of your job, or maybe you need to go back to your product teams and say, hey, you know what, we need to use cloud the right way so I can focus on my ML parts better. So without further ado, let's get started. Here's the agenda. I'll just cover the basic definitions, terms in a few quick slides, current state of ML systems today, ML ops, what and how of it, and the cloud native terminology, what it means. A quick show of hands actually, how many of you know what ML ops is? Okay, fair number. How many of you follow ML ops practices in your core projects, in your day-to-day lives? That's a show of hands now. Okay, so the reason we are following this order, ML systems, then cloud native, and then the 5 principles of cloud native architecture is because we want to know the how first and then the what. The what first and then the how. That is, what is it and how do I do it? Because cloud is mostly the environment we find ourselves building nowadays, and it's also the environment for future. So you need to know how do I build in this environment, and that's what the 5 principles of cloud native architecture covers. Getting started, traditional code-centric applications, had focus on code, and that was the only important component there. Now, as you can see, in ML systems and ML applications, there are 3 major components: models, data, and code. Data, what you feed into it; models, the brain of it; and of course, the code that binds it all together and takes it to your users, your customers, for you to let your users use the ML model, the data that you use to train it. Everything, the output is through code. So all of these 3 components are important. You can't say that, I'll put most of my time to just ML models. Data and models are unique artifacts with their own dependencies and pitfalls. And the joint management of these artifacts, the processes and technologies put together to manage and build using data, models, and code, opens up a Pandora box of challenges that ML teams face hidden beneath the surface. This diagram is from the canonical Google paper, Hidden Technical Depths in Machine Learning, and some of you might already be familiar with it. Data and models, as I said, are unique artifacts, and all of these things, as you can see, the bulk of time and the bulk of expense and effort is not spent in the model training piece here. It's spent in managing the things that make the models work, that makes the model reach your customers, your own users. So where are teams today? Studies today indicate that AI is has a strong potential to improve, scale, and automate decision making in various business functions. While this is widely recognized by a lot of organizations, and nobody is doubtful of the value that AI adds, successful deployments and production grade operations, effective operations, are kind of where we need the most attention right now. I'd also say that they're the bottleneck to gain value from AI. the value right now is sitting with you and not with the customer if you're not able to operate and provide it to the customer. So teams today are, the reason why all of this is a bottleneck is because teams today are still struggling with high degree of manual and one-off work, no reusable or reproducible components, there's poor handoff between data science and IT teams, models don't make it to production, they break, hence there's a loss in effort and a low ROI. This is hindering businesses from taking ML use cases to a newer level, like having more use cases to access, and stopping them for, to have more frequent code updates, have more frequent data updates. When something is so difficult to update, when something is so difficult to edit, you stop innovating with it. This is very logical, right? Because of the hassle involved with experimenting. And imagine something is easy, I would go do it very quickly, right? If I have a book next to me, I may pick it up. But if I have it somewhere else hidden in a box, I will not read it that way. So we want, the goal MLOps has is to make this, to reach what do teams need. And what do teams need is very simple. You can just say it's the opposite of what we saw in the last slide. Well, maybe that's true. We need automated and streamlined processes. And I think I'm going to repeat automation a lot of times. I work with the SRE team and a lot of things here are from the SRE point of view. So we need automated and streamlined ML processes. We need reduced time for change. And I mentioned this in the last slide as well. We want to have a little gap. We want to like smallen the gap that there is between the next set of changes that I want to take to my customers. We want improved deployment frequency, faster time to businesses that they can gain with new ML use cases. We want a shorter lead time and a better collaboration between data science, IT, and data engineering teams. I'll give you an example. I gave you the book example, but coming to tech, let's say I want to test something. I want to have some infrastructure to test something. If my test infrastructure takes maybe an hour to provision and has access issues, testing itself becomes a huge process. When it's quick, you can quickly run, have the infrastructure ready, test it out, and discard it once it's used. Not only does this save cost, but it improves your deployment frequency and also makes your systems more reliable as testing is more oftenly done. Of MLOps and DevOps is the same. We want to shorten the system software development lifecycle to ensure that high quality software is always maintained, delivered, and delivered to your customers, and it is continuously developed and delivered. You want to have high quality software that is developed, delivered, and maintained as well. So how do you build this high quality software? We build keeping in mind the, sorry, my clicker is, I think, yes. We build keeping in mind the 5 principles for cloud native architecture. The good news is that with cloud native, you don't need to deal with the multiple layers of infra that you have. Cloud abstracts it for you and takes care of your operations. Like I can put together all ML use cases for pipelining under Vertex. While this talk is not about Vertex, but you can know more about it on our booth as well. You can meet me there. I'll talk to you about Vertex. But coming to cloud native for now, a cloud native architecture, it is a well architected architecture. Sorry, I want to say that a well architected cloud native system is largely self-healing, cost efficient, and easily updated and maintained through CI/CD. That is continuous integration and delivery. So coming to the first principle, if I haven't mentioned automation already, I want to say that MLOps is a huge advocate for automation. And automation has always been a best practice for software systems. What has changed is cloud has made it further easier to automate not just the infrastructure, but all the components that sit above it. Although the upfront investment with automation is often higher, it is always going to pay off in the results in terms of the effort that you put in. And it favors resiliency and performance of your systems as well. Automated processes can repair, scale, and deploy your apps faster, far faster than humans can. And as we discussed later on, architecture in cloud is not a one-shot deal. And so is the case with automation as well. As you find more ways to update your architecture, you will find more ways to automate your systems. And you will always have new things to automate. But a few ideas of things where you can automate is infrastructure, CI/CD, scaling up and down, and monitoring and recovery. Talking a little bit about all of these, infrastructure. You should automate the creation and of the infrastructure along with the code. So just like how you have a code that is being checked in and there's a pipeline for it, similarly, infrastructure should also have a configuration that you can promote through a pipeline. By removing manual steps from your infrastructure provisioning, you're making your processes less error prone, and this improves the reproducibility and reusability of your apps in the environment. The test infrastructure component example that I gave you, if you have ISE in place, if you want to build a test infrastructure, you can just simply use the production template and discard it once it's used. Next is CI/CD. There are multiple processes involved when your code is updated and you take it to your customers. Building, testing, and deploying. All of these steps should be automated. The reason we want to update is so that not just the promotion of code from you to your customers is automated, but the rollback process is easier as well. Because if I want to update my version or roll back my version, I can just use the last version checked in, and then CI/CD pipeline will take care of it. Next is scaling up and down. If your system scale don't change, then we will not worry about this, but we know that system loads change, and if your system's load are changing, you would scale up. If your system's load are going down, you would scale down. This makes clear sense to save cost, but also make sure that your system is always available. By scaling up, you're ensuring that it is available and your customers can easily access it when there's high traffic. By scaling down, you're saving costs. This also, in a scenario where your applications may have some period where it is not used at all, you may even consider scaling it down to 0. Tools like serverless tools like Cloud Run and GK Autopilot help you with that. But of course, they have other capabilities like auto scaling, auto repairing as well. Lastly, the last bit here is monitoring and recovery. You should be having monitoring and logging in your systems from inception. It shouldn't be a thing for day 100. Like I have set my applications, I'll look at monitoring and logging later on. The reason is that we want to have, we don't only want to get the current state of systems, we also want to be able to measure the overall health of your systems. So if I have some metrics in place, one thing could be to check that how is it behaving right now. But if I want to measure my app's performance later on, I would want to have an overall view of my systems, and that can be done if I was collecting metrics from day one. Lastly, monitoring and logging are an ideal place to attach automation, because for debugging purposes, let's say you have some metric which is telling you that the disk is full and you need to update it, you need to add more disk there. That's the monitoring and debugging bit of it. But you could automate this process. You could have a log-based metric that will look at the log, say that my disk is full, and add more capacity automatically. So not just for debugging, but also for having an overall view of your systems and for being able to automate when there's a failure, so that for your user, it's the same thing. And there's not one more person sitting at all times to do this process of debugging and then fixing the system. It's automated. That was principle 1. Coming to principles 2, being smart with state. Often when we are building complex things, there's intermediary data, like the weights in a neural network after the first epoch, or how many epochs to run, how many jobs are running, etc. This is a maintained state right now, which may need processing later. Cloud native architectures prefer to have the components stateless, as they're easy to scale. If you want to scale up, you just add more of these you add more copies of your app, and since it's stateless, it's not got any affinity with any of your users. It's easy to repair. If you want to repair, you just terminate gracefully the last previous instances and schedule more instances. Rolling back is easier. If you have some issues, you could terminate the current version and start the instances with your older version. And the most important bit, which is stateless components are easier to load balance, because if I have a stateful component, some state will be stored with an instance, and that means that the next time this user comes in, I need to use the same instance. That might overload the instance, but in a case of a stateless app, you're able to schedule any connection with any user. So that's why for reasons for scaling, repairing, rollback, and load balancing, cloud native architectures prefer stateless components. Storing of state is also the most important, the most difficult bit actually, while designing an architecture. So you should have stateless components. But of course, it's not always possible to have stateless components. In that scenario, you need to be very clear which are my stateless components and which are my stateful components. The next principle is favoring managed services. Shipping features quickly is stated to be driving organizational performance, and loading a team with operations where you want them to build features quickly is not a wise resource utilization. Rather than independently installing, supporting, and operating all parts of your application, all stacks of your application, you could use managed services to consume parts of your application as services instead. Let's say you have a MySQL instance, you're taking backups of it, you are making sure that everything is in place for that. But if you use Cloud SQL, which is a managed MySQL instance, in that scenario, you have an SLA from Google Cloud, and Google will take care that you have your backups in place, you have your databases running, and data replication and backups are taken care of from the underlying infrastructure that we have. So that's just an example. But organizations are sometimes, not very keen to try out managed services because of the lock-in feature, and that's a valid concern. But the decision to whether or not to use a managed service is mostly on how is it open source, how portable is it, that means portability, and how simple it makes my life, how much operational overhead does it take from me. For example, Kubernetes is an open source container orchestrator, and it's open source, it's available, but it's a hard to earn skill one, and there are APIs available for everything that is needed in a scalable application, but you still need to call these APIs. If you use a managed service like GKE, the management bit is taken care by you, you have the option to use the UI, so it's making your life simpler, and there's lesser risk because it's open source. You can always port your containers from GKE to Kubernetes if required. But another case could be that there's no open source alternative at all. What do you do in that scenario? In that scenario, we judge, does it make our life simpler? For example, BigQuery does not have any open source, compatible product, but it's used by our customers because it's making their life very easy, and it's very easy to operate. Practical experience has shown that the fear of having to, use managed services, the lock-in fear, rarely outweighs the benefits that one gains in terms of the effort, time, and money spent, when using a managed service and when doing it in a self-managed way. To put things into perspective, here's a comparison from on-prem systems, which is self-managed, to a fully managed environment. As you can see that the time to market is reduced from 16 days to 2 days. The effort is reduced from 15 engineers to 3 engineers, and there's 40% cost reduction. So developing and deploying in a fully managed environment is easier for your developers, lighter on your budget, and a better experience for your customers as well. Coming to the fourth principle, traditionally we put a lot of boundaries, lot of walls, and fortified our perimeters. So perimeter security was very, very important. The idea was that everything outside is not safe, everything inside is safe. But cloud native architectures have their origin in the internet. They have always had some network interaction in between, and we know that there can be sphere attacks, there can be insider attacks. So traditional architectures will not perform the same way on the cloud native architecture. In that scenario, you have to follow the principles. There's a very famous principle that we follow, which is called zero trust network, wherein you're not trusting any component, whether it's inside or outside. The best practice says that every component should try to authenticate to the next component as well. It shouldn't be the case that because it's inside, it's safe to use. The cloud native architecture should extend this idea beyond just authentication to rate limiting and include ideas like, protection from script injections. Each component is a design, is checking what is the component that I'm talking to. And this not only makes your architecture very resilient, it also makes the resulting services easier to deploy in a cloud environment where there may not be a trusted network between your services and the user, because you don't know where your user is sitting, right? So that's why practicing defense is important, and you will hear this term zero trust network a lot. A lot of our services are built with this idea of zero trust network. The last principle here is always be architecting. You know how your models have changing data profiles and they're ever so evolving, so you need to update them and you need to deploy newer versions. It applies to software systems as well. One of the core characteristics of cloud native system is that it's always evolving, and that is equally true of your architecture. You should always seek to refine, simplify, and improve the architecture as the needs of your organization change, as the priorities change, and the capabilities of your cloud provider changes as well. While this constantly requires investment, we should know that dead systems are unable to respond to newer threats and are not able to use the newer opportunities in the best way possible. So that's also one reason to always architect, re-architect, and think of newer ways. And this is especially important in the world of cloud because cloud is ever so evolving. Here's a quick recap of the 5 principles we discussed. We had design for automation, being smart with state, favoring managed services, practicing defense in depth, and always be architecting. I just want to add that cloud native architecture is not there to replace traditional architecture, but they are better adapted to the environment. And actually, cloud is the environment that we'll find ourselves be working in. So that's why we need to use the cloud native ways of things. And as other species can attest, that failure to adapt and evolve and grow is not a long-term option. The principles described above are not a magic formula to have the most out of cloud, but they hopefully provide a strong guideline to you. With this, we have come to an end, but if you want to know more about scalable and resilient architectures, you can read more on this link. This deck will be shared with you. You can reach out and get connected with us on this second link here. And you can get in touch with me over LinkedIn, Twitter. I'm trying to be active on both of these platforms. And I also write sometimes. So here's a quick plug of my blog. Thank you.